Imagine you're holding this like incredibly delicate, intricate logic of a massive software program right there in your short-term memory.
Oh, yeah, you're deep in the zone.
Let's
Total flow state.
exactly, the flow state.
Right.
So you tweak one tiny little rule to fix a bug, and then to see if it actually worked, you have to type this 60-character, highly specific command into your terminal.
Which is just a recipe for disaster.
Wait, one single typo, and boom, your concentration completely shatters. You've lost the thread.
It's the absolute worst feeling.
It really is. So today we are diving into a stack of notes on Haskell programming, and specifically we're focusing on the workflow around test selection.
Yeah, using two tools mainly. Stack, which kind of manages and builds the code, and Hspec, which is the testing framework.
Right. And really, for you listening, the mission of this deep dive is to explore how developers reduce friction when their code breaks. We want to see how they optimize the whole process of rerunning failed tests so they can, stay in that elusive flow state.
Which is crucial.
Totally. Okay, let's unpack this. Because on the surface, sure, we're talking about software testing and command line arguments. But beneath that, we're really talking about human attention.
Oh, absolutely.
Yeah.
We're talking about a universal problem that's just, disguised as a highly technical one.
Right.
We're looking at coding today, but fundamentally we're talking about how efficiently we learn from and fix our errors.
Yeah, no matter what you're doing.
Exactly. Whether you're building strict functional software or, a global supply chain, you are going to encounter failures.
It's inevitable.
Right. And the speed and ease with which you can identify that failure, isolate it, and try to fix that feedback loop completely dictates your success.
Because if the loop is full of friction, your brain just gets tired.
Exactly. You lose focus. But if you make that loop seamless, you can solve these incredibly dense problems without losing your momentum.
So to understand why this specific feedback loop matters so much here, we need to look at what the code in our source material is actually trying to accomplish.
And why it's so prone to breaking in the first place.
Right, exactly. So the developer here is working in Haskell, which is known for being a notoriously strict, purely functional programming language.
Yeah, if your code compiles in Haskell, it's usually rock solid. But, getting to that point requires some really rigorous testing.
It's a journey,
Yeah.
and specifically, the developer is tweaking a parser for various potential headers found in typical Chinese novels.
Which is a whole completely different challenge.
Oh, totally. Because of the wildly varied nature of these headers, their test cases are just constantly failing.
Parsing natural language is a brilliant example of a high-friction environment.
Yeah, think about trying to organize, a massive library where every single publisher across different centuries uses a completely different format for their table of contents.
That sounds like a nightmare.
It is. One book says chapter 1, another uses a Roman numeral, another has, a symbolic character, and another uses a poem before the text even starts. So you write a rule to sort them, and immediately a weird new book completely breaks your logic.
What's fascinating here is that the data is just fundamentally irregular. You aren't just looking for the English word chapter.
Right. You're dealing with character encodings, full width versus half width characters.
Exactly. Lack of standardized punctuation, massive translation inconsistencies. A chapter might be denoted by Chinese characters, or it might just be a floating number surrounded by, obscure brackets.
So the developer has to write dozens, maybe hundreds of mini experiments?
Yeah, test cases. To say, if I feed this weirdly formatted string into my parser, does it correctly identify it as a chapter title?
And when you're dealing with data that variable, writing an elegant rule that catches the right headers without grabbing a random sentence is just a massive puzzle.
It really is.
So naturally, as you tweak the logic to fix one weird edge case, you inevitably break the rule for a completely different header you thought you had already saw.
Right, regression. A test fails.
Yep. Now, to rerun that specific isolated test case in Haskell using Stack and Hspec, our source notes that the required command line arguments are rather long.
Very long.
The developer has to type out this massive string of text just to tell the computer to try that one tiny parser rule again. But, okay, I have to push back on the technology here for a second.
Sure, go ahead.
If it's just a test, why is the command argument so long and clunky in the first place? Why does a modern computer need a 60-character essay just to run a single test?
Well, what's fascinating here is that the length of the command is actually a direct byproduct of the system's power. And really, Its demand for absolute precision.
Wait, so the complexity is a feature?
Kind of, yeah. In a large Haskell project, you might have thousands of tests spread across hundreds of files that are nested deep within various directories.
Okay, that makes sense.
So the Hspec testing framework needs exact directions to find the specific test you want to run. It needs the file path, the module name, the overarching description of the test suite, and the specific string of text that identifies that exact edge case.
Wow, so it needs the full address, basically.
Exactly. When you are structuring a massive code base, that level of precision is incredible for organization.
Right.
But when you are in the trenches debugging a broken regex pattern, the friction of typing or even copying and pasting those long arguments, it totally disrupts your workflow.
It's like you're performing this highly delicate microscopic surgery, and every single time you need a new scalpel, you have to step away from the operating table to fill out a requisition form in triplicate.
Yes, providing the exact serial number of the tool.
It's totally maddening, and because those long arguments are so frustrating, developers naturally start searching for shortcuts.
Oh, always. Programmers hate repetitive tasks.
Which brings us to a really interesting comparison in our sources. The developer experiences a bit of what I'd call elixir envy.
Huh. The grass always appears greener in another programming ecosystem, right?
Always. The source notes point out that in a completely different language, Elixir developer can conveniently rerun a test simply by specifying the line number in the test file.
That is incredibly convenient.
Right. You just tell the system, hey, run the test located on line 42.
Done.
But Haskell, or more specifically the Hspec framework running through Stack, it doesn't natively allow you to rerun tests by line number in that same seamless way.
No, it doesn't.
So to get around those massive long arguments we just talked about, a shorter alternative they use in Haskell is a partial match.
Yeah, which is a very common, quick and dirty workaround.
How does that work exactly?
Well, instead of providing the exact, highly specific 60-character name of the test, you just give the command line a keyword or a short phrase. And the Hspec framework runs any test in the suite that happens to match that phrase.
Ah, okay. It feels like the difference between Elixir giving an exact pinpoint GPS coordinate to a broken pipe versus Haskell's partial match just giving the plumber the zip code and the street name.
That's a great way to put it.
Yeah.
You'll definitely get to the right neighborhood, but it's nowhere near as precise.
Which leads me to a calculation of risk here. Does relying on a partial match risk running too many tests if the test names are too similar to each other? I mean, if I search for header, I might run 49 tests I didn't mean to.
If we connect this to the bigger picture, you've just articulated the exact tension developers navigate every single day.
Really?
Yes. If your test names aren't carefully and uniquely chosen, a partial match is totally a shotgun approach. It will absolutely trigger a bunch of tests you didn't intend to run.
So why do they do it?
Because developers are constantly making these micro-compromises between perfect machine accuracy and human workflow speed.
Ah, I see.
Taking 10 seconds to carefully craft a long, precise command guarantees you only run one test. But typing a quick 3-letter partial match takes 1 second.
Right, it keeps you in the flow.
Exactly. Even if the computer accidentally runs 5 tests instead of 1, the computer's processing time is often way cheaper than the developer's cognitive time.
That makes total sense.
In the heat of problem solving, a programmer will almost always choose the action that requires less physical typing and less context switching. They are fiercely optimizing for their own mental energy.
So they're willingly introducing a margin of error, letting the computer do extra unnecessary work just to save their brain from the cognitive tax of typing a long string.
Exactly.
That is a fascinating trade-off.
Yeah.
But a partial match is still a manual shortcut, right? You are still physically typing something into the terminal every single time you want to check your work.
Yeah, it's better, but it's not perfect.
Right. The holy grail of workflow optimization isn't just a shorter command, it's true automation. And that leads us to the ultimate solution discovered in the source material.
This is the best part.
Here's where it gets really interesting. There is another incredibly elegant option. The developer discovers they can configure a specific hidden file called the .hspec file.
Yep, .hspec.
And by putting a couple of simple flags in there, it instructs the testing tool to focus only on the failed cases. And the absolute best part, once those specific failed cases pass, it automatically runs the full suite again.
It is a brilliantly designed feedback loop. But to truly appreciate it, we really need to understand how it works under the hood.
Please, break it down for us.
So, When you configure that .h file at the root of your project, you're essentially giving the testing framework a permanent set of invisible instructions.
Okay.
You put a flag in there, specifically dash dash rerun, and another flag dash dash rerun, all on success.
Dash dash rerun, got it.
Now, whenever you type the basic incredibly short stack test command, Hspec secretly reads those flags. The system remembers what failed in the previous run by looking at a dynamically generated state file.
Oh, so it has a memory.
Exactly. It uses that file as its short-term memory. It sees, test number 42 failed last time, and it skips the hundreds of passing tests to focus solely on that failure.
Oh man, that's like designing a self-diagnosing complex machine.
It really is.
Imagine you have this massive plumbing system in a skyscraper and you find a localized leaky valve on the 14th floor. You obviously don't want to run a full building water pressure test every single time you tighten a bolt on that one valve, right?
Of course not. That would take forever.
Right, you just want to test that specific pipe. But the very moment that one pipe finally holds water, the building's internal sensors realize it, and it automatically triggers a full system pressure check.
Yes.
Just to ensure your fix on the 14th floor didn't accidentally blow out a fragile pipe on the 30th floor.
That analogy perfectly captures the dual benefits of this configuration. Think about the emotional arc of debugging that complex parser.
Frustration, mostly.
Yeah, you are frustrated. You just want this one specific Chinese header translation to parse correctly. If you have to sit and wait for 500 passing tests to run first, just to see the result of your one failing test at the very end.
It completely drains your patience.
Exactly. This .spec configuration acts as an automatic magnifying glass. It says, okay, let's ignore the noise and just look at the exact spot that is broken.
You get that rapid, immediate feedback.
Right, which provides a crucial hit of dopamine. The test turned from red to green. You solve the puzzle.
Oh, then it zooms out.
Yes, because programming is a deeply interconnected web. A fix to accommodate a full-width character might break a rule for a half-width character somewhere else.
So by automatically zooming back out and running the full suite, the second the failure is fixed, the tool gives you immediate reassurance.
Precisely. You get the speed of localized testing without sacrificing the safety of global testing.
It's incredible how much deep psychological thought goes into the tools used to build the tools. But of course, automation always leaves behind a footprint.
It does. There's always a catch.
Right. And we have to talk about how to clean up after this automated process because it introduces a new wrinkle. The source details mention that this automated process dynamically generates a file.
Yeah, to act as that short-term memory we talked about.
Right. Hspec creates a temporary file on the computer called .hspec failures to keep track of exactly what broke. And the notes are very clear. This dynamically generated file should be explicitly ignored in the version control system.
Which is very important.
And for you listening, version control like Git is basically the master blueprint and history book of a software project where all the developers share and sync their code.
Exactly.
So what does this all mean? Wait, why wouldn't we want to keep that file? Wouldn't it be helpful for other developers on the team to see exactly what tests were failing in the version control system?
This raises an important question, actually, because that is a highly intuitive assumption, and it's a trap a lot of junior developers fall into.
Really? Because to me, more information seems better.
Well, we have to clearly differentiate between the shaded source code, which is the universal agreed-upon blueprint, and dynamically generated machine-specific state files.
Okay, break the mechanics of that down for me. What exactly makes the failures file fundamentally different from the code itself?
Think of the source code as the actual recipes in a high-end restaurant's cookbook.
Okay, I'm with you.
Everyone in the kitchen needs the exact same recipes to cook the meal correctly. Version control ensures everyone has the latest, accurate cookbook.
Makes sense.
Now, the .spec failures file is more like an individual line cook's temporary scratch pad. It's where the chef scribbles, oops, added too much salt to the soup on stove burner number 3 at 2:0 p.m.
Oh, wow. Okay.
That scratch pad is highly specific to what that one developer was doing at that exact second on their specific local machine.
Ah.
If you commit that scratch pad to the shared version control, you are forcing every other developer on the team to download your personal list of temporary localized mistakes.
Ah, I see. It would be like me handing you a pristine, finalized architectural blueprint for a house, but also insisting you keep my crumpled up sticky notes where I misspelled kitchen 3 times and spilled coffee on the math for the load-bearing wall.
Exactly. It's completely irrelevant to the final product.
It just clutters everything up.
It clutters the shared history with noise. But even worse, mechanically, it can cause active conflicts that break the team's workflow.
How so?
Well, if you and I are working on the same projects on different computers, your .spec failures file will look completely different from my .spec failures file because we're working on different bugs.
No, right.
If we both try to upload our state files to the shared version control, the system will panic. It will try to merge my temporary mistakes with your temporary mistakes, creating this chaotic, unnecessary merge conflict.
And then you have to stop working and manually untangle the files.
Precisely. Version control is meant to be the single source of truth for the solution, not a synchronized diary of everyone's localized problems.
It makes so much sense.
By ignoring the .ship as failures file, we allow the automation to do its job locally, giving the individual developer that beautiful, frictionless feedback loop while keeping the shared team workspace perfectly clean.
It is all about separating the messy, highly personal process of building from the pristine product you are actually trying to share.
Absolutely.
Well, this has been such a revealing journey for you tuning in today. We started by looking at a developer wrestling with the chaotic data science of parsing tricky, wildly variable Chinese novel headers.
A huge challenge.
For sure. And we saw how the absolute necessity of precision in Haskell created long, frustrating command lines that shattered a developer's concentration. We explored the calculated trade-offs of the search for shortcuts, comparing the exact line number precision of Elixir to the quick and dirty partial matches that trade machine accuracy for human cognitive ease.
All to protect the flow state.
Right. And finally, we uncovered the mechanics of this beautiful automated loop using the .shake file, a system that invisibly remembers your failures, automatically hyper-focuses on your mistakes to give you a quick dopamine hit, and then instantly pans out to check the health of the entire project.
All while keeping the shared version control perfectly clean.
Exactly.
And, that is why this deep dive matters. Regardless of whether you write strict functional code, manage a marketing team, or are just trying to optimize your personal workflow.
Like principles are universal.
They really are. Finding ways to reduce the friction of trying again after a failure is the absolute secret to sustained productivity. When the cost of failing is high, either in time, energy, or cognitive frustration, we hesitate to try new solutions. We play it safe.
We really do.
But when you architect a system where the cost of failing is incredibly low, we iterate quickly, we take risks, and we discover brilliant answers.
Lowering the cost of trying again. That is a powerful framework. And that leaves us with a final thought for you to carry with you today. We've seen how sophisticated software tools can be perfectly configured to automatically hyper-focus on our recent failures, giving us the quiet, frictionless space to fix them, and then seamlessly zooming out to check our overall stability.
It's an amazing loop.
It is. So if we can build computer systems that are this emotionally intelligent about how they handle the friction of failure, what other areas of our lives or our organizational structures could benefit from this exact same automated focus on the failure, then check the whole system feedback loop.
That's a great question to think about.
Keep that in mind the next time you find yourself frustrated by a clunky, broken process. Until next time.